Okay. So in the class today, we're going to start to talk about a new topic, which is the semantics. So the meaning of data. So today we're going to start with something called RDF schema or RDFS, which is an initial standard to define the semantics of RDF graphs. So the last time we focused on how to represent data in the semantic web using the RDF standard based on graphs. So we spoke about how to use triples to represent graphs and how that's quite flexible and nice for representing data where we don't know beforehand precisely what kinds of data we're going to represent. In RDF graphs, we often have properties, which are the edge labels effectively, that indicate what kind of relation an edge is denoting. We also have classes that indicate groups of resources, for example, movies or series or actors or people or buildings or proteins or whatever it might be. So we have classes and we connect instances to their classes by this special predicate or property, RDF type, defined by the RDF standard. So today's topic, we're going to start to focus on this layer a bit. And it's perhaps the most in-depth layer of the semantic web. Something as well, I think that would be most different to what you've seen in other courses, whereas things like data and queries, you might, they would be quite familiar. We even see them in databases in the semester I teach. We talk about RDF and Sparkle, but this is something that's maybe quite different in this course that you might not have seen before. In terms of the topics we'll talk about here. So the question is, how should we capture logic on the semantic web? What we'd like to do is to be able to define somehow this logic layer so that we can get these kinds of inferences. For example, if A is part of B and B is part of C, then A is part of C. And that would give us access not just to the data, but to the implicit knowledge that we can imply, that the data imply. So how can we do this? So in the semantic web, here, these are expressed as sort of implications or rules. So essentially it's if B capital A, then A part of B. Rather than represent the logic or semantics of the data using rules, the semantic web has proposed to use RDF itself. So what does that mean? It means that we can define relationships with well-defined meaning between classes and properties. Okay, so let's take an example. We see some classes here, town, city, country, person, place, capital, city. It's worth noting that in RDF, normally we represent classes with uppercase, and we represent properties with lowercase. It's a useful convention. So, okay, we have classes here and properties here. And now the question is, what sorts of relationships might be useful to define between the following classes and properties? So we see some intuitive relations between town, city, country, place, for example. And we also see some relations here between, for example, part of, geographically part of, like a place is part of some other place. And has city and these other properties here. So what could we define, for example, between, I don't know, city and place, right? To start with, any suggestions of relationships that we might use here?
Profe, yo tengo una duda primero.
Yep.
¿Por qué family name y person tienen antes del dos puntos F o AF en vez de X?
Yeah, that's a good question. This is called FOF, and this is a very popular vocabulary on the web used to describe people. So if we're describing a person in different data sets on the web, it would be great if we use the same class so that we don't have to figure out later, oh, is this person here, EX1 person, is this the same as EX2 person? So there is a vocabulary called friend of a friend, or FOF, which is used popularly on the web for describing people. And there's also, for example, for country and for town and for city and for place, we could also find these classes and similar properties here in other vocabularies. So it's just to indicate that, sometimes we can find existing what are called vocabularies, which are descriptions of classes and properties on the web. And this is something we'll cover later in the course. But just for now, you can think it's a sort of a well-known class that's used for person on the web of data.
Gracias.
Okay. So what could we define here between these classes and properties? There's a bunch of stuff we could start to define about these classes and properties. But to start with, we could say that some classes are subclasses of other classes. So we can say class C is a subclass of class D, which means that if something X is of type C, then X is of type D. Okay? So as an example, if capital city is a subclass of city, and if Dublin is a capital city, so I say A here, I mean RDF type, so Dublin is a capital city, then Dublin is a city. Okay, so this is a relatively intuitive kind of relation, let's say. So it's very useful. It's one of the most common things that we're going to define between classes. So which classes here would be subclasses of each other amongst this group here? So would city be a subclass of something? So it's like all cities are also something X, right? So all cities are they also countries? No. Any ideas?
City, town, country, y capital city, todos son places, ¿no?
Yeah, exactly. Yeah. So first of all, we have capital city as a city, right? And then we have town as a place, country or city as a place, country as a place, and capital city as well as a place. But I leave this dash because it's sort of implied. If we know capital city is a city and city is a place, then it's sort of assumed or it's implied that capital city must also be a place, right? So we say that subclass is transitive in this sense. So this sort of holds. We wouldn't need to explicitly state this if we already have these two relations. Anything else? I think that's about it. So what about properties? Well, for properties, we can do something similar. We can have a subproperty or property hierarchy, subproperty relation. So if property P is a subproperty of Q, and if XPY, then XQY, that's what this means. So if something is related by P, then it's related by Q, so long as P is a subproperty of Q. So as an example, has capital city is a subproperty of has city, right? So if Ireland has capital city Dublin, then Ireland has city Dublin, right? If Chile has capital city Santiago, then Chile has city Santiago. So we've seen one example of a subproperty relation here between has city or has capital city and has city. Any other examples here? So geographically part of, for example, could be a subproperty of part of. Has city could be a subproperty of geographically part of. Okay, so actually we have, okay, first of all, we have the one we saw in the example, has capital city, has city, and then we have has city geographically part of would be subproperty of part of. And again, we have the transitivity that we saw for class, right? So has capital city is implied through this to be also a subproperty of geographically part of, and also to be a subproperty of part of. And has city is also implied to be a subproperty of part of. So we have like a 4 deep level property hierarchy here. Okay. Any questions or doubts? Make sense? Okay. So we have seen subclass and subproperty. So we've seen how to relate classes and how to relate properties. But how about relating properties with classes? So we'll see two different types of semantic relation. The first is called domain. And we say that property P has domain class C. Then if that holds, if X, P, Y, then X is of type C. So it's sort of like typing the subject of the property. So let's see an example. So if we say that FOF family name has domain FOF person, and if we have a triple, which is Aiden family name Hogan, for example, then we can infer that Aiden is a person. So it allows us to say, okay, family name, if we use this on a subject, then that subject must be within a given class. So, okay, which properties would have which classes as domain here is the next question. Okay, so has capital city, what would we define that on, for example? What would the subject, what type would the subject have?
Country.
Country, right? So in this case, we might want to be a little bit careful. So we could definitely define that. But there are also capital cities of, for example, states or regions or provinces. So if we wanted to use the property in that context, we might want to rather define the domain as something a bit more generic. So something like a place, for example. So full family name person, we already saw that example. Geographically part of, this seems to, since we have the geographically included here, seems to imply that it's defining a place, one place inside another. With respect to has capital city, we could probably define that to be a place as well, right? So we'll come back to that. Sometimes we need to make a decision that's not so clear about the semantics of a term. And that can limit, in some sense, where we use that term, that property, or that class. So, okay, the opposite of domain, in some sense, is range. So range allows us to define the types of the objects of the property in the other direction. So, for example, if has city has range city, and if Ireland has city Dublin, then we can infer that Dublin is of type city. So which properties would have which classes as range here? So in this case, it becomes a little bit clearer. So we have has city, any value or object for has city is going to be a city, right? There's other examples, has capital city as a capital city as a range. Geographically part of, we would assume that to have a range of place. Anything else here? Full family name would have a range of string, in fact, which is not here. Part of could be anything, so it's not really clear what we would define it as. Any other suggestions? Okay, so we actually have some dashed relations here as well. So the object of has capital city is a capital city. But if we say, for example, that capital city is a subclass of city, okay, so we also have has city, for example, sorry, different example. So has city has range city, right? But since city implies that it's a place, then the objects of has city as well, they must be in the class place, right? And similarly for has capital city here, it's sort of implied then that it will be city, that any value for has capital city will not just be a capital city, will also be a city, and it will be a place as well, right? So we have some implicit ranges here based on these range relations and the fact that some of these are subclasses. Okay. Any questions or doubts? Okay, so there is a trade-off here related to the has capital city property that we've seen, for example. There's a trade-off between being more specific and being more reusable, right? So the more specific we are in the definition of our semantics, the more conclusions we can get from the inference from the semantics. The less specific we are, the more reusable our terms will be. So this is a difficult trade-off. This is something I would say on the web, people have tended to be less specific in order to be more reusable. Sort of like the first goal is just to get people to agree on the same terms, defining only some very well agreed upon semantics. But in certain domains, like for example, in medicine, it's more useful to be more specific because you don't need such a broad agreement on the semantics of terms. So for example, has capital city, has domain country. This is actually reasonable to define. Yeah, this is something we could define, but it's maybe a little bit debatable. So the advantage is that now we know that anything that has a capital city is a country. So anytime we have has capital city, we can conclude more things that the subject is a country. The downside, the disadvantage is that we cannot then use that property for capitals of states, of regions, and so forth. So somehow it might be, if we're looking for a way to define capitals and some place on the web has defined this has capital city, we might just use that property to define the capital cities of, I don't know, US states, for example. And that will cause issues because we'll now entail or infer every US state with a capital city to be a country. So there's a trade-off and there's no right or wrong answer. As more specific examples, aside from the semantics of the term, there are also counter examples. The world is a strange place sometimes. So, for example, it would seem more or less safe to define that the class of mayor, anything that's a mayor, is also a subclass of person, right? That seems pretty obvious, but there have been animals, for example, that have been mayors. For example, Bosco the dog was mayor of Sonoma in California from 1981 to 1994. So if we were to define this semantics, it would apply in 99% of the cases, but there will be some cases in which then we can't use that class anymore because we're going to infer that, for example, Bosco is a person. Another example would be, for example, that spouse has domain or range persons. So you say somehow only people can get married. But there's plenty of counter examples. For example, Ulrika Eiffel married the Eiffel Tower in 2007 in some sort of legal way. So in general, when we define things that seem intuitive and seem to apply generally, often there will be counter examples. So there's always this trade-off between being more specific in our semantics and being more reusable. So the more we define the semantics, the less reusable the terms that we define become. So any questions or notes? I mentioned before that there's this friend of a friend vocabulary. There's a web page online that defines the vocabulary. It's been around for a very long time, for decades. So in that vocabulary, they provide classes and properties relating to how to describe people, right? So there is, for example, this property, FOF image, which describes an image that it can be used to represent something. The domain of this property is person, FOF person, and the range is image. So the subjects of this property will be people, and the range will be images. So can anyone see a potential problem with this? Okay, so for my PhD, I was working on finding inconsistent information using reasoning over web data. And one of the most common problems that I found at that time was the use of this property, that essentially people were just reading FOF image. I need to define an image. Why not use FOF image, right? And they would define images of cities, of animals, of buildings, of whatever. And they would say, for example, Dublin image, Dublin at night, right? So this is an image, this is fine. But this is not a person. So this would entail this to be a person, right? So and much of this comes down to the fact that the naming of the property doesn't really indicate that it's for people. And people maybe oftentimes are not going to read the documentation or look at the semantics. So they're just going to see, image, I need an image property, I'll use this, and they won't notice the subtlety. So we should try to choose the names of properties and classes carefully. If we had called this, for example, personal image or something like that, or maybe even portrait or something that indicates a bit better that it's an image of a person, then things would be a bit better. Or we could just drop the domain constraint eventually. Maybe if we see that lots of people are using it for other types in the vocabulary, we could argue that, okay, people are not using it this way, so let's change the semantics. Okay, so RDFS or RDF schema is essentially what we've described. This is the subclass, subproperty, domain, and range are the core of the standard. And it's a web standard. It's been around since the first version published in 1999, then the modern version published in 2004, and a 1.1 version published in 2014. So the core of RDF schema is essentially what we've seen. So we have a special prefix that we use for referring to terms in the RDFS vocabulary. And then we can define subclasses, subproperties, domains, and ranges in the context of that vocabulary. One thing I didn't mention or we didn't see in the examples is that we can define, for example, that full family name takes a range of string, or that full date of birth takes a range of date, right? We can also define the range, the objects to be of data types, to be instances of data types. So that's the core of RDFS. There are some additional elements in there that we'll see a couple of those, but the core of RDFS are subclass, subproperty, domain, and range. Briefly, as to why RDFS calls these things domain and range, when we look at functions in general, in the mathematical sense, if we have a function f that maps instances of x to instances of y, then this here, the set x, for which the function is defined, is called the domain of the function. Y, the set to which it maps elements of x, is called the codomain of the function. And the precise results that it can return here would be the image or the range of the function. So let's say maybe the function f was square root on integers, just to be more interesting. So in that case, x would be the set of integers, y would be the set of reals, and f of x, the range here, would be essentially the set of reals that are the square root of some integer. Probably there's a better example I could have thought of, but hopefully that's useful. So RDFS uses the terms domain and range from this mathematically inspired notation or language, just as a side note. Okay, any questions or doubts thus far? Okay, so if not, we could take an example of building an RDF schema. So the description here is, let's model an RDF schema for movies, including different types of movies, such as horror, comedy, action, some different types of people involved, such as actors, producers, directors, and how they are related. Okay, so this is something we could, maybe do on a whiteboard, but in general, what we'll be looking at is, okay, we have here, we could maybe describe, for example, movie would be a class for sure. person would be a class. And then, okay, we could argue that the genre or the type of movie here could actually be described by a property genre, or we could define it to be classes, perhaps. A horror movie is a specific type of movie, comedy movie is a subclass of movie, action movie, subclass of movie. Actor, producer, and director, again, we could define these as professions of people, or we could define them as subclasses of people. There's various ways, again, in which we could define the schema. So one way in which we can do it is what we describe here. And instead of using the example namespace, I'm just going to use this movie namespace for our new movie vocabulary, hypothetical movie vocabulary. So we here have described different types of movies as different classes that are defined to be subclasses of movie. Then we have different properties like produced, directed, acted in. These are the relations between the movie and the people involved in the movie. So all of these, we will say the ranger movie. Okay. So we don't know, we can't tell just from the produced relation if it's a horror movie or a comedy movie or an action movie. So we'll link the range directly to movie. And we have producers, directors, and actors, and we'll say that these are all subclass of people. And then produced has domain producer, directed has domain director, acted in has domain actor. And here we have a property which is starred in. Okay, this is mainly, I guess, just to exemplify, it doesn't really indicate here so much that we should have this, but starred in is basically for people who are really protagonists who play protagonists in the movie. So we have starred in, domain actor as well, range movie, and we have starred in subproperty of acted in. So this is sort of a complete example using all of domain, range, subclass, and subproperty. So this is a typical kind of RDF schema that we might use. Now, this is not by any means a unique solution. Like I mentioned, rather than define, subclasses of specific types of movie, we could just have a movie class and then define the genre using a genre property, right? Instead of having producer, director, and actor subclasses, we could just have fourth person and then define their occupation to be producer or director or actor using an occupation property. So there's, various ways in which we could define a schema like this. So this is one possible way. Okay. So we saw a bunch of properties at the start, and there was sort of this doubt about part of. What would be the domain of part of? So it's not going to be just a city, because we can use part of in things that are not just cities or places or proteins or philosophical concepts or books, or we can use part of on so many things that it doesn't really have a natural domain. So in RDFS, we have this notion of a class called RDFS resource. It's the class that contains everything, with RDF meaning resource description framework. It's basically anything we can describe in RDF. So RDFS resource is the class of everything. And when I mean everything, I really mean everything. So it's even, it's in itself, a resource the class resource is a resource. So essentially, if we define the domain or range of a property as resource, it tells us absolutely nothing, because we already know that everything is a resource. So oftentimes you'll find this defined just to say, hey, you can use this property on anything you want. It's not restricted. So, yep. We have the class of everything. So we can take a break. I think it's 30 minutes. We can take a break until 10:55. Any questions or comments? If not, see you in about 10 minutes. I'll post the pausa activa in 1 second. Okay. So let's continue. So we have RDFS resource, which is the class of everything. We have a couple of other, what we would call meta classes. These are not things that describe buildings or movies, but rather meta concepts used within the RDFS standard itself. So we have, actually, this is an RDF property defined already in the RDF namespace. It's the class of all properties. It's RDF property. So we can say, for example, that has city is of type RDF property. So all of the instances of this class will be interpreted as properties. We also have the class of all classes, which is RDFS class. So we can say that city is of type class. A common mistake is just that these are in two different namespaces. The RDF standard already defines a class of properties, and RDFS introduces the class of all classes. So it's RDF property and RDFS class, just as a minor detail. Okay, so there is something maybe a little bit strange in that city is a class, but it's also now an instance of a class. So it's sort of like both a class and an instance of something else, which can be a little bit confusing, but RDF and RDFS completely allow this. So whether something is a class or an instance can be maybe a little bit confusing at times, but effectively something can be both. And it's very common for classes to also be instances. They're at least going to be the instance of RDFS class, the class of all classes. But in other cases, we can also have, things that are instances of user-defined classes. So to give an example, would you define oak, the species of tree, as a class or an instance? And I've perhaps given a big hint that in some sense it's both. It's both a class and an instance. So what do I mean by this? I mean that, for example, an oak is an instance of tree species. It's a type of tree species, right? But it's also a subclass of tree, right? So what does this mean? It means that if we have a specific oak tree, Bowthorpe oak, for example, if it's an instance of oak here, what will this imply? It will imply that Bowthorpe oak is of type tree, okay? So classes can act as instances. There's no strong distinction between this is a class, this is an instance. We can have something that's both a class and instance at the same time. Just to clarify that what this will entail is that Bowthorpe oak is of type tree. It does not entail that Bowthorpe oak is of type tree species. Okay, so if we have type followed by type, we're not going to infer type again. Type is not transitive. Okay. However, if we have type and subclass, then we'll infer the type here. So hopefully this sort of makes sense that what we described here, is a good way to model something like oak, or we can consider as well maybe species of animals and so forth. They can be instances and they can be classes at the same time. Any questions or doubts about this? Okay. So in fact, there's no real restriction. We could also have properties that are also classes and this sort of thing. Properties that are also classes is kind of a bit weird, or classes that are also properties. It's a weird case. It's not so common, but classes that are also instances is quite common in modeling. So we describe some different definitions we can have, and we've described what they infer. What are the conclusions we can take from data using those definitions? So in order to automate the reasoning, like for example, we said here, okay, Bowthorpe oak, what we can infer here is that Bowthorpe oak will be of type tree. So this is essentially a reasoning process. And what we'd like to do is automate the reasoning process. So we're going to talk now about how we can actually derive these conclusions. If we have data in RDF and RDFS, how we can actually reason about those data. So first of all, what is reasoning, right? What do we mean by reasoning? So reasoning in a more general context, it relates to deriving conclusions from data, from observations, from premises, from rules. typically in a logical way, but it can also be, there are different types of reasoning. So the first type of reasoning that we could consider in the general case is of this form. All movie directors are human. This is sort of like a quantified statement, or almost like a rule. So I say quantified because it's all. So if you've seen, for example, first order logic before, you know the universal quantification, or all movie directors are human. Then we have a specific fact about Anthony Ferrante as a movie director. So from this, we can infer that Anthony Ferrante must be human. Okay, so this is sort of like sometimes known as a syllogism, but we have a sort of a rule, and we have a fact, and we can apply the rule to the fact to derive a new fact. This is known as deductive reasoning, where we make logical conclusions from the data, from the rules or the premises. Okay, so it's sort of like a very precise form of reasoning. Yeah. There are other forms of reasoning, including, okay, the second type. The first 3 Sharknado movies were great. Therefore, Sharknado 4 will probably be great too, right? So this is not so precise. It's sort of like, we take some observations and we extract patterns from them. If the first Sharknado movies were great, we can sort of imagine the rule that if it's a Sharknado movie, it must be great, right? So this is inductive reasoning. This is sort of learning approximate rules from premises. And this is something you do a lot in machine learning, where you give a bunch of examples, and then somehow the machine learning classifier or the machine learning model has to try to extract some patterns from that to try to predict some outcome. It's not precise in the sense that Sharknado 4 might be crap. We've no way to prove that it's going to be great, right? But so there can often be a notion of confidence or a score associated with the conclusions, in this case indicating that they're not certain, with a higher value indicating more certainty in terms of the conclusion. So this is a second type of reasoning. A third type of reasoning that's sometimes distinguished from inductive reasoning is the following. So Fred saw a movie with sharks and tornadoes. That's like a fact. And Sharknado movies have sharks in tornadoes. So what we're looking for here is somehow a way to explain the observations that we have. So if we see this, we might come to the conclusion intuitively that Fred may have seen a Sharknado movie. And this is neither deductive nor inductive in some sense. It's sort of like we're creating something to explain the observations. So in this case, we have an observation and we have something like a rule. This is almost like saying all Sharknado movies have sharks in tornadoes. And then we're trying to guess the premise that leads to this conclusion, right? So it's almost like going in the opposite direction of deduction, but it's also imprecise, like inductive reasoning. So this is called abductive reasoning, which is where we're trying to kind of guess a premise or an explanation, something that leads to the conclusion that we see. Okay. Any questions or doubts? You could probably also define different types of reasoning. These are the two most common ones are deductive and inductive. Abductive is also spoken about and studied. There's possibly other forms of reasoning one could define. But in the context of RDFS, what we're looking at is really deductive reasoning. We're speaking about deductive reasoning, which is making logical conclusions from rules and premises. So it's a precise type of reasoning. Unlike what we have in, for example, machine learning oftentimes. So it's the only form of reasoning presented here that is certain. It's certain in the sense that if your premises are correct and your rules are correct, then the conclusions you make will be correct. Excuse me. So previously we defined this RDF schema. And okay, so we define this RDF schema, and from the schema, we can make conclusions using deductive reasoning. So for example, if we have a triple, Eric Roberts, starting Sharktopus, the question is, if we have this above schema defined and we're using a property from this RDFS schema, what can we deduce from this triple, the combination of this triple and this schema here? Any suggestions? Excuse me. Okay, so we have Eric Roberts start in Sharktopus, and we see that Sharktopus has domain actor. Start in has subproperty acted in. Start in has range movie, right? So what can we say about Eric Roberts based on the domain here, for example? We can conclude that Eric. Yep.
Yeah, that he's an actor.
Yep. And for start in, we have Sharktopus. So similarly, since the range is movie, we could infer that Sharktopus is a movie. And since start in has the subproperty of acted in, we can assume that Eric Roberts acted in Sharktopus as well. Now, since Eric Roberts is an actor is a subclass of person. Oh, spoilers. We can imply as well that Eric Roberts is a person, right? So we can apply recursively this, and we can infer a bunch of data. Actually, not just that, but we can infer a whole lot of stuff here. So some of it is sort of sort of meta reasoning, or kind of reasoning about the classes of RDFS and stuff like that. The most interesting stuff is down here. So we say that Eric Roberts we've entailed to be an actor, to be a person, to have starred in and acted in Sharktopus, where Sharktopus is a movie. Okay, this is the most interesting stuff. But we can also infer a bunch of other stuff about using the RDFS vocabulary. For example, that a movie is a subclass of movie, a movie is of type class, a class is a subclass of class, an actor is of type class, an actor is a subclass of actor, a property is a subclass of property. This is again is the class that refers to all properties. It's a subclass of itself. So somehow all classes are classes, all classes are subclasses of itself, all properties are subproperties of themselves, and so forth. And this isn't even everything we can conclude. So we can also conclude, okay, just to, which are not shown for the sake of our sanity, because we'd have this highly non-planar graph with edges going everywhere, but we would have to also include that everything is of type RDFS resource, including the properties and classes. We'd have to infer that all classes are subclasses of RDFS resource, because clearly if something is an actor, it is a resource. So that means that actor is a subclass of resource. And that all the RDF and RDFS properties are of type RDF property. So it means, for example, RDF type is of RDF type property, or RDFS subclass is a RDF type property. These are also properties, so they must be in the property class. So there's a bunch of sort of more syntactic stuff that we can entail. The more interesting part is down here is the stuff that really speaks about Eric Roberts and Sharktopus. So these are some of the conclusions that we can derive from the schema and the triple we saw. So Sharktopus is just one movie. So it's just, this is one example of a movie that we could describe. But also we could, have changed the movie, and we could talk about different movies. It's not that we've just defined the schema to define this, to describe this, Sharktopus movie, but rather whatever movie we want, we can now describe using this schema. So in this case, we have Eva Hasberger starred in Dino Shark, for example. And again, whatever movie we use the schema for, we can derive similar conclusions, right? So we have a very similar form. It's the same conclusions, just that instead of Sharktopus, we have Dino Shark, and instead of the actor we had previously, we'll have Eva or Iva here. And the conclusions will remain the same. Okay. So how do we actually apply this reasoning? How do we given an input, which is maybe some data in an RDF schema, how do we actually come to derive all of these conclusions? How do we write them all out? So the simplest is to apply reasoning using rules. So the difference is, at the start I said we're not going to use rules. We're going to use an RDF graph. We're going to describe the semantics of things directly in the graph as if it were a graph. But we can define the meanings of those terms using sort of meta rules. So we're not going to say that, you know, if X is of type city, then X is of type place, but rather we're going to define rules that interpret the semantics of RDFS terms. So these are sort of what I would call meta rules. So there's a bunch of rules here that are not so important, that refer to esoteric or obscure features of RDFS that are things that you would have to maybe know about if you wanted to implement an RDFS reasoner. They're to do with the semantics of data types and these weird container membership properties that really people don't use. So I'm not going to talk in too much detail about them. What I'm going to focus on are these rules here. So we have the first rule is RDF D2, which is here we have an if and here we have a then. Okay, so if the graph contains a pattern that matches these variables, so the question mark here means a variable, it can kind of match anything. So if G matches some triple, doesn't really matter here because we have no constants, so it can be any triple, then what it says is the predicate of any triple is a property. So if we use something as a predicate in some RDF triple in our RDF graph, we can infer that that predicate is a property. Okay. Here we have P domain C, X, P, Y. So if P has domain C and if X uses that property P, X, P, Y, then we can infer that X is of type RDF type, using the sort of turtle syntax of A. X is of RDF type C. Okay, so we have a question mark here. If we have P range C and X, P, Y, what could we infer here? Any ideas? So for example, if we have has capital city range capital city, and Ireland has capital city Dublin, then we can infer that Dublin type capital city, right? So Y type C, right? So we infer that the object here is of type the class, the range class here. Okay, if we have XPY, again, for any triple, we infer that its subject is a resource. XPY here, we infer that its object is a resource. Its predicate is also a resource, but this is implied sort of in an indirect way from this. Okay, so we'll see that in a second. P is a property of Q, XPY. So if P is a property of Q, if geographically part of, or let's say something more interesting, father is a property of parent, and Bob, father, Charles, okay, then Bob, parent, Charles, right? So it would be XQY. Okay, more rules. P is a property, then P is a property of a subproperty of itself. All properties are subproperties of themselves. If P is subproperty of Q and Q is subproperty of OR, then P is subproperty of OR. This is the transitivity of subproperty. So for example, if father is subproperty of parent and parent is subproperty of related to, then father is a subproperty of related to. If something is a class, C is a class, then C is a subclass of resource. If C is a subclass of D and X is of type C, then X is of type D. So if, for example, horror movie is a subclass of movie and X is a horror movie, then X is a movie. If something is a class, then it's a subclass of itself. If C is a subclass of D and D is a subclass of E, then we can expect through the transitivity of the subclass relation that C will be a subclass of E. So in general, these rules describe all of the conclusions. If we apply these rules recursively, we can get all of the entailments or inferences from RDFS. So we need to apply not just these rules, but a number of what are called axiomatic triples that are always true in RDFS. So these are things like that type is domain resource or type has range class. So this says that the value or the object of an RDF type triple is a class. Okay. Domain is a relation between properties and classes. Range is a relation between properties and classes, and so forth. So subclass of is a domain of classes and class, a range class. So subclass of is a property between classes. So there's a bunch of other stuff that's more syntactic. That's not so key. It would be important if you wanted to implement an RDFS reasoner, but or they refer to kind of obscure features that are not so commonly used. So what are these axiomatic triples? They are true statements that involve the RDFS, RDF and RDFS terms. They're sort of like describing RDFS using RDFS. So these are all true statements that we can state. So when we want to do reasoning, what we do is we are given an RDF graph G, and then we add these sorts of true statements to G, things that are always true, no matter what other data we give. We add this list of always true triples to G, and then we apply the rules that we saw previously exhaustively until we don't find anything new. So we just keep applying rules and applying rules and applying rules until we don't find any new triples. Okay, so we add these triples to our input RDF graph, and then we apply these rules here recursively until we don't find anything new. Okay, so this is how we apply reasoning for RDFS. So one question is, will this always finish? So will this process always terminate, right? So it's like, especially here, we say apply the rules exhaustively, adding conclusions to G until nothing new is found. So here we have a sort of a recursion. So there is a danger that this won't finish, right? That essentially will continue finding new things. So will this always finish, or can it run forever? Well, so long as we do not invent new terms, so long as we don't create any new IRIs or new literals or new blank notes, and so long as the triples we consider are finite, these triples that we should add, then the process will end once we have all combinations of terms as triples. So what I mean by that is that G is a set of triples. Okay, so it means that it can't contain duplicates. And it has a fixed RD, so it has a fixed length of 3. So it means that we have sets of triples. We have at most 3 elements in each triple. We can't have duplicates. So as long as we don't start inventing new terms, at some stage, all of the known terms, we can, create all possible triples with all of those terms, right? And then we stop. There's a point at which, we'll just have, in the very worst case, we'll have created a graph that has all of the terms, all of the combinations of terms, and then there's no way to continue, right? So as long as we satisfy these conditions, the process will finish. Any doubts or questions about this part? Okay, so this is the kind of initial part of logic. This was kind of the initial standard defined for this to handle this sort of logical layer. There are still certain things, actually, in neither of these rules we can currently express using RDFS. So we can't say that part of it is transitive, and we can't define inverses. So RDFS is just the first standard. There's a second, much more comprehensive standard called the Web Ontology Language, or OWL, that goes much more into depth in terms of defining these sorts of semantics of things that we describe our data with. It even reaches the sort of limits of computational power in the sense that the types of reasoning that we'll be able to do, a computer won't be able to do them. if we try to define everything. So there is this sort of general idea that if we continue adding more things to RDFS, if we keep going in the same direction as what we saw, we'll reach the limits of computation, and we'll eventually reach a point where reasoning will become undecidable, which means that you can't just program an algorithm to decide to get all of the conclusions, or to know if something is a valid conclusion or not. So we'll be going in that direction. In the next class, we'll just speak about the features of OWL, and then we'll talk a little bit about the limits of computation with respect to what's known as knowledge representation, this idea of representing knowledge in a systematic way to automate reasoning over that knowledge. So yeah, so this was an initial standard, first defined in 1999, I believe, modern version in 2004, an updated version in 2014. So this is an agreed upon web standard. It's quite widely used on the web, and it describes mainly what we've seen in this class here. Okay, so yeah, in the next class, we're going to deep dive into another standard that allows us to describe even more detailed semantics. So RDFS is really just a more simple form of semantics, or shallow semantics. With the next topic we'll talk about, which is OWL, we'll see how to define much more detailed semantics. Any questions or comments? Okay, one thing as well that I will, I keep kind of postponing things and saying that I'll talk about them later in the class, but the idea here as well is that we can publish this on the web. Yeah, so we can get some people who are expert in movies, expert maybe on semantic web and RDFS, and we can sit them down in a room and we can get them to define a schema like this, and we can publish it on the web. And then essentially the idea is that in other documents, in other places on the web, they can reuse this great vocabulary, this great schema for describing movies. And then by referring somehow, by using the terms of this vocabulary, we can, for all of the data that use that schema, we can reuse the same schema to reason about that data. So in an ideal case, this schema here is published on the web, and there could be millions of other websites and documents using that vocabulary, where if somebody wants to somehow do reasoning over that data, they can grab the schema and they can apply the semantics to deduce more conclusions from the data. Okay, if there's no more questions or doubts, in the lab on Wednesday, we're going to see this in the lab on Wednesday. So you're going to have to make some definitions in RDFS to derive some conclusions that we give you from some data that are given. So, okay, if there's no questions or doubts,